Hello and welcome again to some solution chemistry. This is the third part of my series on this, and we've studied about factors that make solutions, what they are, and we studied concentrations and how we can record how much solute is inside the solvent. And finally today we're going to look at what's known as a colligative property. Colligative properties are properties that can be altered by making a solution. So everything we're going to talk about today is involving something that is a pure solution, or not pure, but a solution. So colligative properties, they are properties that depend upon the impurities that are involved with a solution. And some of these are vapor pressure and boiling points, melting points, and a new one, osmotic pressure. Now, because these interactions between the solute particles and the solvent particles, if the solute particles are attracted to the solvent, then it makes it so that it's more difficult for that solvent to release molecules into its gaseous phase. So if the intermolecular attractions are higher because of these solute particles, because there's an attraction between them, then it's going to make it more difficult for the solvent to actually release those molecules, because it's going to be adding to the intermolecular attractions. We saw before that intermolecular attractions, the higher they are, the lower the vapor pressure. So one of the things that we can definitely see, a colligative property, is vapor pressure, and we can see that whenever we have a higher concentration of an impurity, it's going to cause the vapor pressure to decrease. Of course, someone sat down and figured out a mathematical law, a proportion for this, and it's called Réault's law. And this may be on the AP cheat sheet. I'm not sure, can't remember off the top of my head. But here you can see all it is if you want to find the pressure, the new pressure of the solvent's partial pressure, then you can take the original vapor pressure and just multiply it by the mole fraction of, watch out, the solvent. You see that? This is all for the solvent. So we take the mole fraction of the solvent times its original vapor pressure, and we'll get the new new vapor pressure for that mixture. So yeah, again, the solvent. Notice that subscripts are all the same. It's the solvent that's causing the vapor pressure. All right. Now, when you alter the vapor pressure of something, then yeah, it's going to be changing other things, like its freezing points and its melting points. So we can see in this graph here, the black line is the original, and that's of the pure liquid. And then this blue line is representing the lowering of the vapor pressure due to the addition of some impurity. So up here you can see that if that was lowered, so if I drop this line down, drop that whole curve down like this, you can see that now where the temperature and new vapor pressure intersects with 1 atmosphere, which would be its boiling point, you can see that that is higher now than what it used to be. And over here on the freezing end of things, as we drop that vapor pressure curve down, you can see that now where this intersects with the vapor pressure line at 1 atmosphere, the vapor pressure of the solid line intersects at 1 atmosphere, it is now considerably lower in temperature than what it was before, and that would be its new freezing point. Okay, so here's what we say. We say that boiling points are elevated and freezing points are depressed. So I think of it this way. If it's already hot, it's going to get hotter. And if it's already cold, it's going to get colder. So hot things get hotter, cold things get colder. All right. So here's our formula that we can use to determine the temperature change when something is has an impurity mixed with it. And if we take a look here, we've got one constant, Kb. Kb would be its its freezing point depression constant, and you can see they just come in lists like this with different solvents. Again, this is all set up for the solvent because it'd be the solvent that is actually doing the freezing. We have our little m here that stands for molality, and we've seen that in the past, worked with that in our past video set. And then we have a new thing here, this I, which is known as the Van't Hoff factor. And the Van't Hoff factor down here, as it says, is the number of particles that something dissociates, that the solute will dissociate into when it's dissolved. So, and then the last thing I'd like to point out is this is a change in the boiling temperature. So this is just going to represent how much the temperature has changed. You have to be smart enough to know whether I need to add this to the boiling point or subtract this from the freezing point. Okay, so you're just going to be given the change. So you might end up with an answer of like 1.5 would be your change in the boiling point. That doesn't mean that the temperature it boils at is 1.5. It means that I'm going to add 1.5 to the original boiling point to get my new boiling point. And freezing point depression, same formula. Now we have the Kf as our new constant, the mole freezing point depression constant. Boy, that's a mouthful. And same deal there. We're going to subtract it from the normal one. We got our Van't Hoff factor, our molality, the whole deal stuff. Okay, so not only does delta T depend upon how much in molality and what the substance is, the solvent is for those Ks, but it also depends upon the impurity itself and how many particles dissociate when that impurity is in there. Now, if it is something that is a molecular substance, a non-ionic substance, then the Van't Hoff factor is always going to be 1. AP uses the word non-electrolyte. Remember, an electrolyte is something that would break up and dissociate when it was dissolved. So if you see that word non-electrolyte, don't be scared of it. That's a comfort word. That means Van't Hoff factor is 1. You don't have to worry about it. However, if it is a substance like sodium chloride, let's say, salt, like we added to the ice the other day, then when that mixes with the water, it is an electrolyte. It will dissociate, and when it dissociates, there will now be 2 particles floating around in solution, a sodium and a chlorine. So in that case, the Van't Hoff factor would be 2. This is trying to show that. So if we have something here that is an ionic substance, then it's going to break up into its individual ions. So for every unit of this that I put in there, NaCl, I'm going to end up with a sodium and a chlorine. I'm going to end up with 2 units of impurities. Whereas something over here, like some ethanol or something like that, then that unit stays together, and so my Van't Hoff factor is just 1. Now, sometimes, even though we'll have something in there and the NaCl should have a Van't Hoff factor of 2, we don't always have that show up experimentally. And they say their reason for that is that not always do all of the particles split up into its ions. Sometimes these ions get together while in solution, and then they stick together with the water molecules all solvating it. So this isn't a number that's always exactly true, using like 2 for the Van't Hoff factor for sodium chloride. And we can see that how much it is off is actually dependent upon the concentration of the sodium chloride itself. Because the more sodium chloride I have in there, the more likelihood that you're going to get something like this happening. The more dispersed it is, and the more further away these particles are kept from each other because there's dilute, the less that will happen. So, of course, someone has put together charts and has studied all this and earned their doctorate's degree this way. And over here you can see that in the charts, as we decrease the concentration of the impurity, you can see that the value gets closer and closer to the actual Van't Hoff factor. Here's potassium sulfate. That would break up into 2 potassiums and a sulfate. So our Van't Hoff factor should be 3, but you can see it's less, especially as you get to higher concentrations of this. And the third one, fourth one that we're going to look at is osmosis. And osmosis is just a process where you have some type of a membrane that blocks certain particles. Usually it blocks the impurity, and it allows water to flow through the membrane itself. In biological systems, these membranes can be natural ones, say like the cell has natural membranes. So this is just a graphic showing you that the solvent itself is going to pass through the membrane, and the idea is that it's going to try and dilute and create the same concentration on both sides of the membrane itself. And something has to force the particle, the solvent particle, through there. And that is forcing the solvent particle through the membrane is what we call osmotic pressure. We use pi to represent this osmotic pressure. And here's our formula. And the formula here you can see is MRT. If we take M here, that's molarity. And with molarity, we're going to use the moles over volume. And R here is our gas constant, so that's going to be in liter, atmosphere, mole, Kelvin. So temperature's got to be in Kelvin. And moles is okay. Volume's going to be liters. And then you're going to get a pressure has to be in atmospheres. So pay attention to your units with that. Okay? When it gets to its equilibrium, where the osmotic pressure is same on both sides, we call that an isotonic solution. And in biological settings, a lot of times they'll refer to isotonic solutions because when you store things like cells, when you're creating cell lines, like I used to work at the University of South Florida where we grew our own brain cell lines as I was working for a professor who was doing Alzheimer's research. And we had to make sure that the medium that the cells lived in was isotonic with the cell itself. If it didn't, if I had higher concentrations of my medium that it lived in, then what would happen is that the water would come out of the cell to try and dilute the medium, and that would create a cell that would just get sucked all the water out of it, or a crenated cell. Likewise, if it's the other way around, then you will end up with a cell that if you have its medium be too dilute, then the water will rush into the cell to try and equalize the concentrations, and it will cause the cells to actually burst because they'll get too big. It'll be like a balloon and it'll burst. And you see this happen to you when you are like in, let's say, a bathtub. And when you're in a bathtub, that water is considerably, a lot more dilute than the concentration of the salts inside of your cells. And so you swell up, right? And you get like a plump where your cells start to get big and they swell up. Likewise, when you're in salt water, then your skin gets all dry, right? Why does it get dry with salt? Again, the concentration of the salts are much higher now than what's inside of your cells, and so your skin cells lose water to the salt water through osmosis. Alrighty then, here's an example of a problem. And with this one, it says that we have some antifreeze, and it consists of this ethylene glycol, and there's our formula for it. And check out these words right here: non-volatile, non-electrolyte. Non-volatile means that it has pretty high intermolecular attractions, so it's going to interact with the water around it and hold it together. And non-electrolyte means that it's not going to dissociate, so that our Van't Hoff factor is just going to be 1. So those are comfort words there. Means I don't have to worry, even though they look big and ugly. Okay, so I got 25% by mass, the solution of ethylene glycol. Let's start out with our formula here. I know, and I'm looking for what, boiling point? So I know that the change in the boiling point is equal to IM, which is molality, and then Kb, which is our constant. So I here is our Van't Hoff constant, and we just said a moment ago, because it is a non-electrolyte, that this Van't Hoff constant is just going to be equal to 1. So I got that covered. Next thing is our molality. Well, I have a percentage, but I don't have molality. And so we're going to play that trick that we saw the other day. If I have a mass percentage, and what I really want is what? Moles of my ethylene glycol. Let's just call that EG, over kilograms of water. And that's what I'm shooting for. What do I have? Well, I have a percentage. So remember, our trick was to take 100 grams of the solution. And in 100 grams of the solution, I know that I would have 25 grams of the ethylene glycol. And I would have 75 grams, or 0.075 kilograms of my water. Let's use our molar mass here. And I should be able to come up with this, and I find out that my molality of this is about 5.37. I got my second piece of information. And then the third piece of information that I need is just the constant itself. And for water, that constant is 0.51. Again, I get this from a chart. On the AP test, it would be given to you. It's degrees C per molal. And so the 2 molals are going to cancel out, and I'll be left with something in degrees C. So crunch, crunch, crunch. And in the end, I get an answer that is 2.7 degrees C. So now that tells me that my boiling point is going to change 2.7 degrees Celsius. You have to be smart enough to know, it's a boiling point. Those increase, and so I need to see, I got an error here. This is boiling point elevation, huh? I have to know that the boiling point is going to be elevated, it's going to increase, and so my new boiling point then is going to be 102.7 degrees C. Because this is water, it boils at 100, so now it's 102.7. Okay, let's try another one. In this example, we're looking at one that has calcium chloride, which is an ionic substance, and so we're going to need to take into account that Van Hoff factor. So this time we're working on melting points or freezing points, and if I want to solve for how much it changes, I'm going to use my formula. Delta TF is equal to the Van Hoff factor times molality times our molal freezing point depression constant. And in this case, I'm working with calcium chloride. So calcium chloride is CaCl2. And when this dissociates in water, see, it's ionic. So when it goes in water, it's going to dissociate. It's going to break up into calcium ions and 2 chloride ions. So when it dissociates, it's going to dissociate into a calcium ion and 2 chloride ions. Or this one piece is going to break up into 3 pieces. That is where our Van Hoff factor comes in. So for the Van Hoff factor, I'm going to use 3. The Van Hoff factor tells us how many pieces the ionic substance dissociates into, how many ions it dissociates into. For molality, we can do our calculation for this. I have 25 grams of the calcium chloride, so that's going to go on the top. And it has a molar mass of 111 grams per mole. That's going to get me moles on the top. And on the bottom, I have a half a kilogram of water. That'll get me my molality. And then I just need my molal freezing point constant. And for water, which this is, it is 1.86. When I crunch all this together, my final answer comes out to 2.51 degrees C. And again, this is the point where you have to be smart about this and recognize that this is a melting point depression, so it's going to be lower than the actual melting or freezing point of the original substance, the pure substance. And so if the pure substance was 0, water is 0 degrees, then it's going to depress by 2.5 more degrees. So then my new freezing point is going to be at minus 2.51 degrees C. Okay, and the last of these is osmotic pressure. And I'm going to not only show us how to use the osmotic pressure formula, but I'm also going to show us a very common requirement of the AP, and that is to find the molar mass of something. Remember, that's been a thread that we've seen on lots of our labs. We try to determine the molar mass of the compound, and that helps us in trying to identify the things that we can't really see. So we can calculate molar masses from colligative properties. And so that's what we're going to do with this particular problem. We're going to find the molar mass using an osmotic pressure. So here I have some protein, and it's dissolved in some water. and it tells us what the osmotic pressure is. Remember, the osmotic pressure is the pressure that is pushing the solvent through the membrane during the process of osmosis. Our formula for this that we're going to use is equal to pi, which is the osmotic pressure, is equal to mRT. So I have my R, which is a constant. I have my temperature, which is going to be in kelvins, and I have my osmotic pressure. The only thing I don't have is my molarity. So I'm going to solve this for molarity. So molarity is going to be equal to pi over RT. Now my osmotic pressure is in torr, and R, of course, is liter atmospheres, so I need to make sure that I have this torr converted into atmospheres. To do that, I'm going to take my 1.54 torr, and I'm going to divide it by 760, because there are 760 torr in an atmosphere. I'm going to divide this by R, and this will end up in atmospheres up here. I'll take my R, which is our 0.0821, that's liter, atmosphere, mole, Kelvin. And then 25 degrees Celsius is 298 Kelvin. Now I've plugged all my units in here because I want to show you things canceling. I have atmospheres are going to cancel there. Kelvin's going to cancel here. And I'm going to be ending up with liters over moles in the denominator. So what that's going to do is end up flipping up top. And I'm going to end up with a unit that is moles per liter, hence the molarity. So as I did all that, crunched it all out, it came out to 8.28 times 10 to the minus fifth. Moles per liter. So how do we get from here to finding the molar mass of it? Well, we've done this in the past where we've had some grams of something, or the mass of it, and we've had the moles. Remember that the final unit for a molar mass is grams per mole. So if I can, out of this thing, which I have moles, can somehow get it to grams, find out how many grams I actually have, and then, well, I have the grams, I'm sorry. If I can get this to just moles, then I can take the moles here, and I have the grams from the problem, the 3.5 milligrams, and that should give me my answer. So let's try that. The way to get moles out of my volume is, remember, we can take the molarity times the volume, and that would be equal to moles. So my molarity I have times my volume. It's got to be in liters. 5 milliliters is 0.005 liters. And when I multiply those two things together, I'm going to end up with 4.14 times 10 to the minus 7th moles. And I know that I have 3.5 milligrams. So 3.5 milligrams, we've got to turn that into grams. So that would be 0.00350 grams. And now just dividing those two, I'm going to end up with a pretty big number, which proteins usually are, 8.45 times 10 to the third. So you can see out of these depressions and changes to things like osmotic pressure, we're able to come out of it with a molar mass, which is key for us because that's a way we identify substances, kind of like one of its fingerprints. All right, now this time, no joking. I have one for you. There's your answer. Okay, I hope this has worked well for you. I wish you good luck and have fun.